Thank you for your introduction. So now I'm going to talk a little bit about basic fluid mechanics and computational fluid mechanics. So I hope you will enjoy it. Up to now, you had quite a lot of really advanced talks about nuclear uh, physics applications and advanced systems with advanced geometries and quite complicated topics. So now, just for a difference, I think it's a good idea to make a break and kind of get down to earth and review some really basic concepts before you move on again to work with advanced numerical methods and study really complex geometries. So it's always a good idea to start with really basic things and review some maybe well-known or maybe well-forgotten subjects. I'm quite sure that every one of you who are sitting here and listening today, all of you had some fluid mechanics courses, maybe last year, maybe a few years ago. So it's nice to get a little review to refresh maybe forgotten but very important equations, such as, for example, continuity equation and Navier-Stokes, because fluid mechanics is about solving these equations. And how do we solve them? Of course, when you went to university, you solved lots of equations by hand with pen and paper. But unfortunately, in real life, so many equations are which cannot be solved in this way in an easy manner. So that's why we need numerical methods. And there are so many of them, and you are going to work with a lot with finite element methods. But there is an older method, which is known as finite difference method. There are many, many of them, but the concept is the same. And we will talk a little bit about them. Are they still useful? Are they out of fashion? Do we still need them? And how do they work? And if we will have time, we will maybe see a little bit about Python resources, how we can do numerics in Python. And with a little focus on a special finite element method, which is called McCormick rule, a so-called predictor-corrector method, and how it can be applied to solve Navier-Stokes, compressible Navier-Stokes for a two-dimensional cavity flow. So this is the outline of what we're going to do today. I apologize a little bit for some technical difficulties. I am using multiple screens and somehow I could not remove this tiny piece of my presentation. So I hope you still can view in a proper way. So what we need to do is the so-called differential analysis. The basic theorem, which kind of runs its background for everything, is the so-called Reynold transport theorem. A few weeks ago, I have been grading like hundreds of exam papers from fluid dynamics course, which I'm teaching. And that's what I'm doing. And there were quite a lot of what's going on in fluid dynamics. It can be kind of boils down to these conservation laws, which is conservation of mass, conservation of energy, change of momentum, and all we need to combine with the motion of fluid particle in order to go into Navier-Stokes. So these are our basic ingredients, which will produce all this richness of fluid dynamics. So just like in making a recipe to cook a meal, we need some basic ingredients, without which we cannot achieve the full description. So is with fluid dynamics. We need basic physical quantities to combine them to describe the behavior of the system, which we are going to study. And the most important thing with fluids is, of course, that they are not rigid bodies. When students start to work on fluid mechanics and get introduced to this Reynolds transport theorem, many find it very theoretical and mathematical and sometimes even unpleasant to work with. And of course, it's because we don't have a lump of mass, which behaves like we're used with Newton mechanics. We have a lump of mass, and here come forces, and they act on it, and they change the momentum, and it moves, and we can compute how it moves. This is how we're used to think from school about physics. But fluid mechanics is fundamentally different in this way, is we don't have this lump of mass. What we have instead is what I call an observation window through which this mass of fluid, if it is gas or a liquid or a combination of these, it flows through this observation window, which we call a control volume. So that's why we have, when we introduce these quantities like mass, linear momentum, angular momentum, all these important physical quantities, they are what we observe flowing through this observation window. So this concept, what drives all these formulas and why it looks so special. We have to integrate over a control volume and see what happens when these quantities are flowing through it. So Reynolds transport theory is, in its most general form, is written like this. It says that we have a quantity n, big N, extensive quantity, and just to remind you, it was a long time ago when you learned this, extensive quantity is something which scales with mass. It's proportional with mass, like, for example, linear momentum, because it's mass multiplied with velocity. But there are also other quantities which are called intensive quantity. And this I defined with the little eta Greek letter. And this is of quantity, but per unit mass. It is mass independent. An example of such a quantity, for example, temperature. If you have a kilogram of water at 20 degrees, if you double it, you have 2 kilograms of water, it doesn't become 40 degrees temperature. It's still 20 degrees. Some properties are inherently intensive, such as temperature, and some we can make them intensive by dividing by mass. And so Reynolds transport theorem just tells us that the rate of change of quantity n, it may be energy, for example, it may be mass, equals to the rate of change of this quantity inside the control volume. That's why we're integrating over CV, which is control volume, and of course multiplied with density and in infinitesimal volume, and how it changes with time, plus the rate of flux of this quantity through the control volume. And this, every physical quantity can be written or expressed in this way. So this is very fundamental theorem. So for Newton's law, we are also expressing force as change of linear momentum, because as you remember, Reynolds transport theory expresses everything as a rate of change. So force, if you have to write it as a rate of change, what is it? Yes, it's a rate of change of linear momentum. So that's how momentum equation enters into fluid dynamics, and this is very important for all our applications. So it can also be written in such a way as to be put into Reynolds transport theory. And so is conservation of mass. And this is an equation which we're going to use quite a lot, which will give us many important quantities. Again, the rate of change of mass is the rate of change of mass inside control volume plus flux of mass through the limits of control volume. So putting it into Reynolds transport theorem, we will get this result, given that the mass cannot disappear and become nothing, and it cannot appear out of nothing. So what it says is the change of mass inside plus flux out of control volume, together it is zero. Conservation of mass, that's what it says. Putting it another way is that the change of mass in the control volume is the same as the netto flux to or from control volume. This is a very fancy mathematical way to say that in order to put something into a volume, you need to move it through its boundaries, which is a very commonsensical result, but when you write it in a mathematical way, it looks like this. Well, of course, just remind you very fast about some very easy special cases. When we are so lucky, when we work with incompressible flow, we get a very simplified version of this equation. And when do we need to talk about such cases? Actually, in many engineering applications, when we are working with liquids at normal conditions, room temperature, normal pressure, lots of liquids behave in this way. So the special case is actually applicable to many different applications, so we don't need to write it off. Steady flow has a little bit different. Steady flow does not necessarily mean incompressible, so that the density may change, and our equation modifies a little bit. And another simplification that all students love when we do exercises, it's a uniform flow. When it is written in its basic form, density multiplied with velocity integrated over area is simply the same as a volume flow multiplied with density. We don't have to integrate, which actually says flow in equals to flow out. Again, a very commonsensical result, which is written in a special way. When can we use such simplification? Is it too simple? Actually, it's even if it's a simplification, it is very much applicable into many engineering situations, because uniform flow, what does it say? It says that the velocity is constant over the surface of outlet or inlet surface. When we're talking about flow through pipe systems, we talk about cross-section of the pipe, and flow through such cross-section is actually very often very close to uniform. Why is that? We know that there are viscous forces which will force the flow to become non-uniform, that we will have zero velocity close to the pipe walls because of viscous forces, and the maximum velocity in the middle. But this beautiful picture is often valid for laminar flows, which means that the flow must be very slow. In many practical situations, the velocity is often high enough, so the flow becomes turbulent. One might think that turbulent flow is very complicated because the velocities are chaotic, and the movement of particles is complicated, and the streamlines cross and have complicated shapes. But then we're talking about averages, then it's very close to uniform velocity. So strangely enough, this very simple special case is actually very applicable to many practical real-life situations. So we don't need to write it off, even if it looks very basic and simple. We actually use it all the time. So now let's get those laws together. From Reynolds transpose theorem, we get the conservation of mass, which only says change of mass inside control volume plus Netto mass out of control volume equals to 0. And try to use this on a tiny infinitesimal control volume. That's what we do when we need to study the flow in detail. When we're interested to describe the fluid mechanics on as a little scale through complex geometries, we need to do this infinitesimal analysis. So we are choosing a tiny control volume with small size, with infinitesimal sizes dx, dy, and dz. And looking at it, what happens when it is placed in a velocity field. And the velocity field, we have to assume that it's continuous, and it can be varying in 3 spatial coordinates, x, y, and z, and it also can be unsteady. That means that we also have a variable time. So what do we do when we want to describe how it behaves on an infinitesimal control volume? Let's say we know how it behaves on the left side of this infinitesimal control volume, but we don't know how it behaves on the right. So what do we do in such cases? And how do I express, for example, velocity component in x direction? How do I express density? Only thing I know is that there are continuous functions which are well behaving. That means they do not explode, they don't go to infinity, they don't have discontinuities. So what I am going to do is to do the oldest trick in the book. And this contribution is due to a man called Brooke Taylor, who actually lived in 1600s and died in 1731. So this is a really old contribution to science. And his famous book, Methodus Incrementorium, from 1715, it really laid the foundation for numerical computations of today. So we owe this guy a great deal, and I think if it was like this, we could take patent on mathematical formulas, then probably his great-grandchildren would be multi-billionaires today if they could take royalties for every time we are using this famous Taylor expansion, because this is like the background of all numerics we are doing. So to find this Netto flux in x direction, and we have to do this in all directions, we use this famous Taylor expansion, which you recognize here, where to develop an expression for density at the right-hand side, at the right side of this fluid element. We have the flow into the element, we have the minus because it's a flow into, and these contributions from the right-hand side. And there we expand in the Taylor series the density and the velocity in x direction. So far, so good. And we have to do it to multiply this out, and we get a long expression. What is good about this way to do it is that even if it is long, a little bit boring, but it's always the same time, it always works. Why does it work? Why can we just stop at those two first? Why couldn't we take more terms? Because you probably remember that there are in infinite series. Well, it all boils down to our initial guess that the function is continuous and well behaved. That means that the terms which are higher than second order Taylor expansion, they are small. So that means that for badly behaving functions with lots of discontinuities, we cannot do it. But we can do it here, and after rearranging these terms, and an exercise you probably have done before, but you will see that we can rearrange them and make them more practical. We have the dx dy dz, which is this infinitesimal volume. And so can we do for all directions, for x, for y, and for z. Exactly the same exercise with Taylor expansion on one of the opposing sides of this cubic volume element. And of course, we combine it in one equation, and we see we have the same pattern, and instead of writing out this, we can write it in a more compact way with Nobla operator. So we are almost done, we're almost finished. We need to combine this mass change inside the volume. And we get this. which is our continuity equation, which is one of these ingredients we need to achieve a complete description, which is Navier-Stokes. We have the continuity equation, we have the Reynolds equation, and we will also see combine it with forces acting on the particle. So this is a continuity equation in its most general form, because it is also applicable to non-steady and compressible situation. So we can write it in a more, as I told you, we can write it in a more compact notation, so we don't have to write out all those partial derivatives. So this is one of our main ingredients. Again, if we are so lucky as to work with liquids such as water, oil in non-compressible situation, we can simplify this a lot because density is constant, and we are left with this easy relation because density does not change. However, a steady flow, which is compressible, we cannot get rid of density, but we can get rid of the derivative of density with respect to time. So there is another variation, but only for steady flow. Can also be written in a compact form. But when we are going to do numerics, we will actually need to go into the details and look at the partial derivatives, because we will need expressions, how to discretize them. But when we are writing equations and want to save time, then of course use the compact notation. So now we need the final ingredient. Okay, we have the conservation of mass, we have the Reynolds transport theorem, which gave us the conservation of mass. And now we need to express forces that work on this particle. And to describe forces, how do we make force? We need an expression for acceleration, because force is mass times acceleration. So how do we do it for a fluid particle in a flow? And again, we have this problem, which we don't have when we are doing normal mechanics. We don't have a lump of mass which moves under because of action of forces. We have a fluid particle in a flow, which is moving in a flow, and it's following a path. Let's say it's moving through a three-dimensional space along a path, and at the time t, this particle will have a particular velocity. Velocity to this particle is given by the velocity field it experiences at that instance of time, at this position given by x, y, z, and of course the time with t. Okay, so here we are at this instant. But of course, an instant later, time has changed with delta t, a little infinitesimal change. And what happened? Well, what happened is that the velocity has changed. How did it change? Well, it depends through x, y, and z. So the positions have changed, but also the time has changed. So we have 4 contributions to change in velocity, both the time and position. So that's what makes it more cumbersome. We will get lots of contributions and long expressions. So as the particle moves, the flow change because of location and because of time change. These 2 factors we have to remember. And we need to express them. And this expression is not going to be very beautiful, because we have to write out dv is total infinitesimal change in velocity. What we actually do, it's like we're doing partial derivatives. The chain rule of derivative. The first is partial derivative dv dx times the little change, infinitesimal change in dx. and the same in y direction, dv dy, change of velocity with respect to y, and multiplied with change in y position, and the same for z position. And the last and the final, which is different, where we have explicitly differentiated v with respect to time. So that means that if we have a steady state, this last term will disappear. We will not have it. But for an unsteady state, we cannot neglect it. We have to take that too. And then, of course, we have to go from dv to dv dt to make acceleration. So we will divide all of those terms by dt, and what you see in second line, what happens is, of course, that we notice that dx divided by dt is the same as actually velocity in x direction when dt is very small. And so we can simplify that. And so with dy dt, it is the velocity in y direction, and dz dt by dt is velocity in z direction. So it kind of simplifies it a little bit, but not really much yet. So we have to keep all those velocities. But then what we have achieved with all this writing, it looks like some mathematical tricks, but actually it has taken us a step further. We have then defined a quantity, which is very important for us when we're going to do fluid dynamics, is we have expressed acceleration for a fluid particle. This is something we always do when we are simulating a movement through all complicated geometries, because inside the black box, there is Newton's law, mass times acceleration. So acceleration, it is this. And for a fluid particle, it looks like this, because it has the three first terms connected to spatial changes, and the last term, which we put here, which is connected to change because of the change of time, because of non-steadiness of this flow. So how do we call this quantity, the particle acceleration? They have several names for it. We have a saying in Norwegian that dear child has many names, and it definitely is the case with this derivative, this acceleration. It can also be called particle acceleration, but it's so imprecise. It can be a particle of a solid, so it should be another name. So they are sometimes called substantial derivative, material derivative, and what I prefer is actually to call it a total derivative, because it reminds us that we are taking all the contributions into this expression. All those factors go into. So this is our substantial derivative, and these are the parts of it. So the first lump, because it all has to do with spatial derivatives, it is often called convective derivative. And its origin is the particle moving through space. And maybe it's easier to remember because it's a convection. When we have temperature differences in the liquid, the particles start moving, so it's called convection. So maybe that's why it was called this. And the last term, it also has a name, of course, and it is called local acceleration. And at the first time, it sounds like a really bad name, rather a misnomer, because, I mean, how call it local? It's time dependent, so it has something to do with time. But if you think about it for a few seconds, then it actually is a good name, because local corresponds to a particle standing, being in constant place, and time passing and making acceleration because of the passage of the time. So it's actually a good description. The particle is in one location and experiencing acceleration because of the changing and unsteady flow. So this is local and caused by non-steadiness of the flow. So now we have all those three components. So now we have our ingredients, and now we are ready to make Navier-Stokes equations because we have an acceleration for a particle. So now we know how to write it up. There are very, very many ways to derive Navier-Stokes equations. And of course, there is no time to go through them all and find the ways here. But with our basic ingredients, which we have now, we are ready to make Navier-Stokes equations because we know how to write up the acceleration for the particle. And as it always is, I think it's very good to always keep in mind this basic. What we actually are going to do is Newton's second law. It's always the Newton's laws. Only we will do it in differential notation. And we are doing it for fluid particle. And Navier-Stokes, they are named after two physicists, a French physicist or engineer or mathematician. At that time, you could be all of them together, named Claude Louis Marie Henri Navier, and an Irish mathematician, Sir George Gabriel Stokes. And what is remarkable about these two persons is that they have developed this equation at the same time, around the first part of 1800s, and they did it independently of each other, which is quite a remarkable feat without collaborating or anything. And it was obviously enormous breakthrough at that time. Sadly, they could not actually solve them, and you will soon see why. So now let's make these equations and go the way via Newton's law for the fluid particle. So let us see which forces are acting on a volume element. Here is our volume element. As always, we do the same trick all the time. We're placing it in a coordinate system and define a point inside this infinitesimal control volume. Let's say it's a cube with sides dx, dy, and dz, and all surface forces which are acting on it. And what kind of surface forces can be? They can be, for example, pressure. It's the most classical example of a surface force, and then also viscosity. So first we are defining normal pressures, defined with sigma, and acting on the left and the right side of the element. It's only in x direction. Of course, it's not the whole story, because we will also have the forces, the shear forces, which are acting along sides, the foremost and the backward side, which are giving rise to shear tensions, and so on the top and the bottom side. So here are all six forces acting. So to get from tension to force, we have to, of course, to multiply with the area of the side. That's why we have all those dx, dy, dz, and so on. And it's quite a lot. So we have normal and shear stresses. And we have also to remember the directions of this. Positive direction is always defined as pointing outside of a surface. So we have to take consideration of that. And we have to sum them up. So now comes the boring part. And of course, I forgot to notice to mention it for you. But of course, we are doing this age-old trick of Taylor expansion. That's how we can write these forces. And the first time the students see it, they get kind of shocked because it looks so much. How can we know that this is true? I mean, how can I say that this surface shear stresses and normal stresses, how can I say that it is like this? But it's always this same assumption that all these functions, both the functions for normal stresses and shear stresses, they have to be continuous and well behaved. They don't have any singularities. They don't have any sudden breaking points. So we are able to make a Taylor expansion. So again, great credit to Brooke Taylor from 1700s for being able to do this. Because this is our first guess. When we don't know the expression, at least we know that it can be that it has a first order derivative. And so we just turn out the machine and summing up all those forces, all these 6 contributions from every phase of this volume element, and combining them in a single equation. So here they are, the normals and the shear forces, up and down, and left and right, and top and bottom. So here they are all together. And if you noticed, you go a little back, you have the pluses and minuses. So there are lots of stuff which is going to disappear. And what is most important is that these quantities themselves, which we don't know, they're disappearing because of the minuses, but the derivatives are the one which are left back. And this is the important part of here. It's not important to follow all the details so closely, but at least we see that we are left with derivatives. And those are the surface forces. And surface forces are all those forces which are not acting through the mass center, such as pressure, viscosity, and such. And of course, we also can have body force. And the most typical body force we are experiencing is, of course, the gravity. And maybe our system is oriented in such a way that the gravity has a component in x direction. Usually we don't orient it like this, but here for the sake of completeness, we take a component in x direction. Which other body forces can we have in our situations? Not so many, actually. It's gravity, or if we are working with special kinds of liquids, for example, the ones which are susceptible to magnetic forces, then we will have electromagnetic forces inside this contribution. For magnetic liquids, they are also body forces because they work through mass center. So we have added all forces in x direction. And now we have set up all the forces. It's this basic, it's in Newton's second law, which we have in mind. That's what we are doing all the time. So now we have set up all the forces, and we know that that must be equal to mass times acceleration. So now we need our ingredient, which we made before, the particle acceleration, because this is what is created by these forces. So all these forces together, they are working on our particle in order to give it acceleration. So we're putting this together, combining with what we found was acceleration for the particle in only x direction. That's when we did this, the convection part and the local part, when we are taking derivative with respect to time. So here is the first component of Navier-Stokes equation, because that's what it is. But we need to know a little bit more. And here comes another very important assumption. This one is due to Newton. And this is a special type of dependency of shear strain and deformation, which is related to velocity gradient in liquid. And it sounds like many words, but you recognize it immediately when you see it, because this is one of the first things you have learned in your fluid dynamics courses. And this was this relation between shear strain and deformation, which could be related to this du, dy. If we have a velocity in x direction, and y was the coordinate, for example, for difference between two parallel plates. if you remember these parallel plates and the flow between two parallel plates, there was a velocity profile, which was a straight line. This is like what every fluid dynamics book starts with. And then we could talk about viscosity. So there was here, this viscosity comes in, is there is this proportionality relationship between stress and deformation, which in turn is related to this du dy, because it's quite difficult to measure deformation in a liquid. So it's very impractical quantity. So it was very clever of Newton to find this relationship. So we can, instead of trying to measure infinitesimal deformations in a liquid layer, we could instead look at how velocity in the liquid layer behaves. So this is a very important thing. So we can substitute it, but it's not enough, because we need to do something with these shear stresses. And generally, we can also have these types of relationships for other types of strains, for other dimensions, and other velocity components. So for xy or ix, that means that there is a strain in x direction. It can be used the two components. And so is for the z and for the x. So this Newton's relationship can be generalized to other directions as well, because we have a three-dimensional system. But when can we use these relationships? They are not for every kind of liquid. So we have to remember that they are applicable only to liquids which are so-called Newtonian liquids, which have this linear relation between strain and deformation and the velocity profiles. Which liquids are not like this? We have liquids that are becoming more dense when subjected to larger shear forces. And opposite, we have liquids which become thinner when subjected to larger forces. And you have seen examples of that. The first one, which becomes much more viscous when subjected to forces, is like you mixing starch with water, and you're getting a mixture which is becoming harder when you press on it, so you can literally walk on it. And in the opposite scale, you have the ones which are becoming thinner when subjected to stresses, and these are stuff like paints, which we want to be more less viscous when we apply them to make them flow better. So ketchup is something, it runs when you shake it, because when you shake it, you are applying shear stresses to it. So it becomes more, it flows more easily. So for those kind of liquids, we cannot use these ones, because they're only defined for Newtonian liquids. Those are non-Newtonian. And we are not completely there yet, because we need also some kind of relations for the normal stresses too. And it can be shown, it actually been done quite long ago, in 1845. That means it was done at the time Navier and Stokes were working on these equations, so they could utilize this, that we have this relationship for normal stresses. And this is, we are very happy that we can prove it, because we need to put the derivatives of velocity vector into, because it's very hard to work with these shear stresses and normal stresses as they are, because these quantities are very hard to measure, they're impractical. So we want to put the derivatives of velocity into equation, because then we will probably know how to solve it. So all these useful relations combined, we will finally get the Navier-Stokes equations in all their beauty and glory, and they look quite daunting. This is only the x component, but you will have a similar in similar way, contributions for all other directions, for x and y directions too. So as you can see, such an equation is not what you can solve with pen and pencil. And unfortunately for Navier and Stokes, they could not do it either in 1850s or so, because they didn't have the computing power. So what instead they have been doing for many years is solving some special cases of this. For example, non-viscose case, when viscosity can be set to be neglectable, or very, very small. So all these horrible partial derivatives just magically disappear, and we are left with Euler's equation, and so on. But let's just not lose it. Just keep in mind what is it we are always doing. No matter how complicated this equation looks, it is still just Newton's second law for a fluid element. But it also shows in which ways fluids are much more complicated than solid bodies in this respect. So here, this is mass multiplied by acceleration. I hope you can still recognize it. It is this material derivative, total derivative with all those terms. And this is simply sum of forces working on this little element. That's what Navier-Stokes equation actually says. And this is gravity's component in x direction, mass forces in x direction, and those are simply surface forces. Everything that comes from pressure and viscosity and these viscose deformations, which are created by the stresses working on it. So that's what it is. And if we are working with a liquid which is can be magnetized, then we will also have some electromagnetic forces into here too. But this is rather exotic. So before we still have some time. So just to sum it up, here is what Navier-Stokes is. And this is one way of deriving these equations. You have probably seen several more, but this one is the one that goes like through very basic down-to-earth approach, is simply thinking about Newton's second law and forces, sum of forces, which act on a fluid particle, and creating the acceleration of this particle and deforming it at the same time. So as you can see, we cannot simply solve it. Okay, if we neglect the viscose effects and we have an equation which is much more manageable, of course we can also restrain ourselves to 1 or 2 dimensions. And we can also simplify it a little bit by looking at the steady state equations, and we get more and more simple and manageable equations. And those of them you have probably done quite a lot of before. But what happens when we at last have to attack the full Navier-Stokes? What do we do then? When there is both compressible and viscose fluid, and it's also non-steady, and we have to do something. So now that's where the numerical methods come in. So now we will start to look at this part of this huge field of study, numerical methods, and we are only looking at the little part of it, which is finite difference method, or methods, because there are many of them. And of course, we can only look at a little subset of those. We will talk a little bit about how we make discrete mesh, and how do we handling the derivatives, because that's what it's all about. And what kind of truncation error they have, different schemes. and just see a little part of the huge variety of these methods. So here we go. What do we do when we do final difference methods? Probably most of you, if not all, might have done some programming course during your studies, and surely heard about like Euler's method, maybe even Runge-Kutta method. And it was based on dividing a domain into small pieces and approximating a solution from a solution known at one point, and then using some way of educated guess to find a solution in the next point. And this was done in a step-by-step manner. We had to go through some amount of points to cover the whole domain. It was done in using some kind of loop. You wrote probably a programming code which would loop through these points. So that's actually what lies beneath all those finite different methods. Walking through a grid. So what we're making is making a mesh. If there are 2 dimensions we're looking at, and it's a good idea to start with 2 dimensions. Let's say we have x and y, and we are making the simplest possible grid, just dividing with equally spaced mesh points. So if we have 2D velocity field, and we have x component of velocity, which we normally call u, and it will be dependent on x and y. So let's, for the first time in the beginning, only look at x, y dependency. So we have to discretize it. What does it mean to discretize? It just, as this figure shows you, define a point on the grid. Here it marked with P, and it is defined with numbers I and J, which I refers to the steps in X direction, and J refers to steps in Y direction, and the steps are equally spaced. So we can only know about the values in those steps, but of course not in between. And we are using these indices, I and J, just like coordinates on a map. So if point P is ij, then the point to the right is I plus 1 because it's the next step in I direction, but the same j, so j doesn't change. If we go upwards, then the j is plus 1, incremented with 1. If we go downwards, it's decreased by 1, and so on and so forth until we have covered the whole grid. Okay, so we have made the grid, but how do we find the values? And of course, this is Taylor again. Again, we are using this 300 years old, almost 300 years old approximation by Taylor, which again is based on an assumption that our functions are well behaving and they are continuous. They don't make any huge sudden changes, and they are possible to find the derivatives. So here we are writing up the full Taylor expansion for a neighboring place and a neighboring value of u. It is based on a value in the point ij plus first derivative in point ij times time step in x direction, because we are developing in the x direction, then second order derivative with respect to x, and time step squared divided by 2, and so on and so forth. And we are dividing by larger and larger number. It is given by factorial function, if you remember expression for Taylor. So each and every term which comes later becomes smaller and smaller and smaller. So we need to use this expression to find an expression for derivative. And this is very easily done. simply by solving out for du dx. So from that, if we just move it on the left-hand side of the equation and rearrange the terms, and the first we see, which pops up, this is the finite difference representation, the first dominating term of this derivative. So du dx in a given point, ij, it is given by the difference between two neighboring points and divided by a time step. But wait a little, it's exactly what derivative is. If we could have, you remember how we defined the derivative from your basic mathematics course? It's just taking the limits between two neighboring values and dividing by the step between them and letting the step go to zero in mathematical sense. In reality, of course, we cannot make delta x zero, we can make it very small. So that's why this is not exact value, but approximation. It's a finite difference representation of first order derivative. But what about the other terms? They have not disappeared. They are not, we cannot put them to zero, and they are not zero. But all those combined terms, they are called truncation error. And the size of this error is, of course, determined by the largest of these terms, because it's the one that dominates. And when we look at this, we see that the largest term here, which is second order derivative multiplied with delta x divided by 2. So that means that the largest error goes like delta x. And this is not really very good. And we will see soon how we can fix it. Now, if you have noticed, the expression we have made for the first order derivative, and the first order, because it's called first order because it's truncation error, as we have said already in delta x, it's a first order in delta x. And there is another name for this, and there'll be lots of names like this now. It's called a forward difference. And why is this forward? Because we are using u is being evaluated at I plus 1. So we are going forward. We are taking the rightmost neighbor of our starting point. We're going to the right, forward. So this is called forward. But of course, there is nothing that tells we cannot do it other way. We can also go backward and go to I minus 1. This is what we do. And we are obtaining in the same way. We're obtaining a backward difference and a corresponding expression for the first order derivative. And again, these following terms, we are putting them all into this truncation error term, and we are using this big O notation. Or stands for order, and order is delta x to the first because it's the first term. Sorry? Yes. So that's how we can obtain the forward order. But we are not happy because of this truncation order is really, really bad. What does it mean? That means that we really need to make this delta x very, very, very small in order for this thing to converge. And having a step very small means that we will need very many points to walk through. And it makes our code will run slower. And again, if you remember, if you ever done a numerical project, you probably all have tried this Euler's method. And this is actually what it is. It's Euler's method. It's the first order derivative. And you all know that it works very poorly, especially on functions that grow fast, which have something of an exponential behavior. So you know that the further we go, the larger the discrepancy becomes. So it's really a bad idea. So we have to do a trick. And the trick is very simple. Now we have made a forward difference and a backward difference, right? And they are very, very similar. If I just move a little bit back and See, what is making difference is those signs, because when we go forward or backward in Taylor, you have pluses here we go forward, minuses when we go backward. So some things here will cancel. And this is exactly what we're doing. You can do it yourself to convince yourself that it works on pen and paper, but we jump to conclusion and observe that if we subtract Taylor expansion backward from forward and solve for the differences, then we are solved for this du dx. That's what we want to find. And what we are left with are much higher order term, because the previous terms were cancelled. They had the minus. The one had the plus, and another had one minus. So they got cancelled. And what we are left together will be higher terms in truncation error, higher terms in delta x. So this is what is called second order central difference. It is second order because, of course, it's second order in delta x. And it is a central difference because we are going one step forward and one step back. So we are symmetrical about our starting point. And we have to divide with 2 delta x because we are taking 2 steps. And this is somewhat more precise. Why it is like this? Well, we can take in about it as somehow a weighted average. When we are using only forward or rearward difference, or backward, another word for it, we are trying to predict one step ahead, or we are building upon one previous step. But when we are doing central difference, we are combining one step back and our prediction from a step ahead and kind of taking an average of this. So it is much more, gives a better guess for the derivative than only going in one direction. And this is also why we are getting a better precision. So central difference is better than forward or backward. But all of them are actually being used in many, many numerical schemes. And this was nice and well using this for first order derivatives. But as you remember, our equations, Navier-Stokes, they were also higher order derivatives than only first ones. So we cannot stop here. We need to find a way how to handle second order. And again, our fantastic Taylor series again comes to rescue. And this time there is another trick. Instead of subtracting 2 Taylor series, we're adding 2 Taylor series. And then we are getting cancelled the first order derivative terms because they were with plus and minus for forward and backward Taylor. So they're getting cancelled. And this is good because we don't want them. We want this second order. We want expression for this one. And again, we are rearranging this. I'm skipping this, and you can easily get convinced that this is what we're getting by simply moving this term here. And here we're getting this famous and easily recognizable, for those who have done this before, expression of a second order derivative in x direction. And here we need contributions from forward step, backward step, and double contribution from the middle point, and divided by delta x squared. And you see that the surviving term in which giving us truncation error is delta x to the fourth, but because we have to divide by delta x squared, so we end up also with delta x squared as order of precision, which is good, but could be even better. And of course, needless to say, you can do exactly the same for the second order derivative in y direction. It will be exactly the same way forward, and the expression will be very much the same. except that you have to notice the indices. Now it's not I, it is the J which is changes, because it's the one corresponding to Y direction. So here is another very, very useful formula. And finally, what about if we have mixed derivatives? Because if you remember from the Navier-Stokes, they have du dy and du dx, and you can second order, but there are different variables to differentiate to. But it's actually will do much of the same thing. We can write Taylor expansions for partial derivatives too. It is possible to do. So it's kind of the same way. And for backwards and forwards with respect to y, and then subtract them from each other. So, and in order to achieve expression for second order derivative by dx and dy at point ij. And knowing that we have a relation for the u dy and forward, using this, we will arrive to final expression, and combining for forward and backward, substituting them into our expression, and we will achieve this. After cleaning up some terms, it just takes too much space to write them out, but you can do it and convince yourself if you want to in your spare time. But I recommend that we accept this as this result. And here we have the combination of forward in I and j, forward and backward, forward in I, backward in j, backward in I, forward in j, and backwards in both of them, and divided by 4 delta x delta y, because we are mixing now x and y derivatives. And what about this order? And the order is as before, because we are doing the same trick as we have done with ordinary derivatives, subtracting two Taylor expansions. And so we get the same precision, a second order in delta x and delta y. So quite a useful expression, and this is the one which we use quite a lot of it when we are doing Navier-Stokes and all kind of equations which mix partial derivatives. So now we have lots of ingredients to make numerical methods. And of course, it's only a tiny little part of how they can be made, how they can be discretized. So let's present a little zoo of these discretization techniques. Here is the first one is this, maybe the simplest, the first order forward difference with respect to x. It takes into account two neighboring points, ij and forward in I. We can also have a first order backwards or rearwards difference with respect to x. And I think it's very useful to illustrate them graphically like this. You easily see which way it is moving and which indices to use when you are going to write a code for this. And the second order central difference with respect to x. The one which gives you a better precision because it's central difference. It takes account of 2 points symmetrically centered around our starting point. And to the more complicated ones, second order derivative. It is called second order central difference with respect to x. Here we are having contribution from 3 points. The middle point with the double contribution, and you remember it was with -2, and equal contributions from backwards and forwards points. And in the same way, we can handle the first order forward and backward differences and in y direction. Anything that changed, that is the orientation of this scheme. This is called a sometimes it's called computational molecule, and it's because of this way of drawing it like molecules. Very good technique to visualize what is happening. So of course, such a molecule need to move through the whole domain and cover all points that we need in order to solve equation on the domain. And some more, we had a second order central difference. Again, with respect to y, so our molecule turns 90 degrees. And same with second order, derivative with respect to y. And to illustrate the last one, we have formulated the mixed difference when we are mixing derivatives with respect to x and y. It looks like this. We are involving the points forward in x and y, backward in x and y, and covering all those four corners, but not the one in the middle. It's not in the scheme, it's not contributing, but all those four. And by computing these four values, we are getting some kind of weighted average where all have the same weight and giving us a second order precision in this way. So, okay, so we have discretized in spatial directions in x and y. But sometimes we also need to do something more. We also need to take time into consideration. For example, if we are looking at the flow which is non-steady, then we have to put time dependence into our equation, and this is Navier-Stokes does have time equation. So we have to find a way to move forward in time. So this is something we call time marching direction. This is going from step in time, step number n. We are introducing time step delta t, and with time step we propagate our solution to different steps in time, n+1, n+2, and so on and so on. And for every time step, we are computing, solving the equation on our spatial grid. Here, for simplicity, it is only drawn an x coordinate, but we are going to look at what x and y. So for every time step, we have to cover xy grid and solve equation there, loop through all these grid points, and when we are finished, then we are ready to propagate to the next time step. And when we are building up our solution in this matter, it is called explicit method. When we are moving from one step to the next, there is one unknown. So this is how it is done. For step T, we are covering our xy domain with all these i's and j's, which you have looked through and solved the equation and found numerical expressions. And then we are ready to go to the next step. Here is our continuity equation. And this is a typical situation. We are having x and y dependency and time in our situation because we have time dependency. So this is how an explicit thinking about explicit method. There are implicit methods when we are cannot just move to the next step from the previous. We have to incorporate previous time steps in the same computation. So we are not solving one equation, but the whole system. So we have to diagonalize a matrix with a system of linear equations instead of only one. But this is not. This is outside the scope. We are focusing on implicit methods, and we have when the next step builds on the previous step alone. So how can we use an implicit method? And here I want to introduce something which is called McCormack scheme. McCormack scheme are special in a way that this is so-called predictor-corrector method. What is special about it is that it is not only built on one step, but on two steps. Again, to illustrate why it is necessary, it is maybe a good idea, again, to compare with this Euler method, which we all have tried. It's like the first numerical method we ever learned and found that it was very wrong. And the reason why it was wrong, because it was made on only prediction of one single step. So if the function was varying very fast, for example, growing very fast exponentially, then this Euler method will lag behind more and more as we are trying to progress to a solution. The more we try, the more wrong it gets. And this is because it was based only on one predicted value based on one previous value. And such prediction doesn't work so good because it is not corrected. So here, are we doing something else? We're doing something called predictor and corrector. So for example, if we have a density, we can compute it for one time step based on the first order derivative approximation. And before we move to the next step, we are using a new step, which is called the corrector, where we are putting our computed density as an input before we can move to the next step. So predictor step, in our case, it will be, this is the predicted value with bar over to identify it as a predicted value at t plus delta t. This is based on the previous step and the first order derivative multiplied with delta t. Looks like Euler's method. And this is made by forward differences. Such a thing can be done not only for density, but for all other quantities of interest. Just like you see here, velocities in x and y direction. So our predictor step is actually, in principle, as simple as the forward difference of first order derivative. If we look back at our equation, how it looked, we have time derivative of rho and first order partial derivatives. So we will hopefully recognize it in its discretized version, where we are putting in first order forward differences in u, density, and v, and discretize it. So it's the same equation, only in discretized version. This is our predictor step. The next step is the corrector step, where we are again doing this almost the same thing, but now you see all those quantities with bar over. They are the ones that are computed in the previous step, in the predictor step we're putting into, but now we are walking backwards. And we are using backward differences in I and j and in all those quantities of interest. So it's the same equation, it's discretized in the same way, only backwards. Why are we doing this? It is because we need to incorporate a correction. We made a prediction based on step forwards, and we're using this prediction and step backwards to compute the same thing, because we're not going to have exactly the same results. And now we have two values, one based on forward step and one based on backward step. If you think a little bit back, how do we improve our precision when we wanted to compute derivatives? We went from backwards and forwards, we combined them to make a central difference. And this is exactly what lies in the core of predictor-corrector method, McCormack, that we are making a weighted average of backwards and forward step. And this is from predictor and corrector step. And this is what we will do finally. Finally, we are combining them. Here is our predictor and corrector step, and dividing them by 2. We are taking equal average. They both contribute as much. And finally, when we found all those, we do this for all quantities, for density, for velocity, and so on. And finally, after all this, we are ready to advance to the next step. And this time, we are using this average value with the result of predictor and corrector. It sounds quite a little bit much, maybe, but it always think that this basic expression we have done for central difference, this is very similar to what we're doing, where they're making a weighted average of derivatives evaluated at backward step and forward step. So when you think about it this way, then it's actually quite easy. We are taking an average of 2 guesses. That's what predictor-corrector is. Of course, there are much more advanced versions of this approach. There are methods, for example, called Runge-Kutta, where you don't do one step, you do actually 4 steps before you can move to the next time step and computing derivatives and then taking a weighted average of these 4 points. So this is not the limit of how advanced you can do it, but actually this scheme works quite well for many applications. And now I'm seeing that we have been sitting and I've been talking for quite a long time. So in a few minutes, we will take a break. But before we do it, maybe I can suggest you to just review these formulas and look at them so you recognize how we discretize these derivatives, because it's the same equation, only these derivatives are now written out in our discretized form. They are simple first order forward differences. You see, you recognize it by seeing I plus 1, j plus 1, and so forth. This is the predictor. And the important part, this is the corrector, where we are using these predicted values. You see there these bars over for density, for velocity, for all those quantities. But instead, now we have the minuses, j minus 1, I minus 1, where we go backwards in space. So now we have computed these derivatives in 2 ways. And of course, not only for density, but for all these guys, U and V, and so on. And then finally, before we take this simple step, it looks like Euler. It is actually forward step, first order. But before we do it, we need to take average so that the mistake we do is minimized, because we are now basing our prediction on 2 points instead of 1. This is what makes this method better than simple forward and backwards method. It's the same thinking as when we are introducing central difference. And I can recommend you a very great book on this subject, where lots of discussion of different ways to discretize Navier-Stokes, and several examples. I found it in Fluid Mechanics by Kundoko and Dowling. Very good book, and an example I would like to show you after the break. It's also very well described there. And the fully discretized Navier-Stokes is shown how it is done on predictor corrector method of McCormack.